A CAF failure is where copper corrosion within a printed board leads to a short. It is electromigration of the copper from anode to cathode between two conductors of different potential. This is the opposite of the SIR failure, where a short grows from the cathode to anode and typically forms a well-known dendritic structure. The phenomenon is sometimes referred to as cathodic anodic filament because, conversely to SIR, electrochemical induced short grows from the anode to the cathode. The short is also a metal compound, a salt, and needs to be hydrolyzed to conduct. Hence, a CAF short can vanish when removed from a damp heat environment.
That's my guest, Graham Naisbitt, next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
My guest, Graham Naisbitt, has an extensive working history in the electrical and electronic manufacturing industry. Graham was the IEC 1906 Lord Kelvin Award Winner, IEC TC91 WG2, 3, and 10 maintenance leader of 4 standards. He is the vice chair of the IPC 5-30 Cleaning and Coating Subcommittee, overseeing 15 IPC Development Committees. He's received 14 IPC Standards Awards and is a BSI British Standards Institution ELP 501 member. Graham is a specialist in insulation resistance testing, ionic contamination control, solderability, conformal coating materials, and application systems, including cleaning, inspection, and test. I spoke with Graham from his home office in England. Graham Naisbitt, thanks for being my guest today on Reliability Matters. I really appreciate you being here today.
It's very kind of you to make the invitation, and I'm very pleased to accept.
Well, I can't think of someone better to invite on the show to talk about the subject matter we're going to talk about today, which is CAF. Now, 3/4 of my audience just went, what? CAF? Like young cow? Like, no, we're not talking about beef. We're talking about conductive anodic filamentation. But before we get into that very exciting subject, you've got some contractors at your house today. You've warned me that we may hear some drilling and some hammering and some, who knows, contractor sounds. I'm not hearing it on this end, but if we do hear that, we know that your house is making progress. So that's a good sign.
Indeed. Hopefully it will not interrupt us.
Well, as we talked about before we started the show, the great silver lining of this work at home thing that a lot of people are doing is we're having a lot of online meetings. And during these online meetings, everything from cats blocking the screen to dogs barking to children running in the room to contractors at the house, life happens at home. And when we work from home, we bump into life. So I think it's an accepted event in modern times.
Indeed, although it has saved a fortune on travel costs, especially for me. My financial controller is very pleased that I'm working from home, because when I get on an aeroplane, I prefer to turn left if I can stretch to it. But
I do too. Yes, exactly. I remember when I travel with my team, like if we're going to a show or something overseas, my wife always goes, "How can you sit there and everyone else sits there?" Like, look at the stripes. I've earned those stripes. Spent a lot of thousands of hours in the back. So if I can, score my upgrades and cash in my points, I will be glad to make a left instead of a right.
Exactly.
So, Graham, you are the founder and principal at G3. Gen 3, I should say. Gen 3 sounds like Generation 3. Was there a Generation 2? Was there a Gen 1? Where did Gen 3 get its name?
Originally, I came into the industry back in 1979 when there was an opportunity presented itself because Humaseal, the coating group, were looking to expand their operations in Europe, especially through the UK. Primarily, I guess, through the military sector that we have always enjoyed here. And I thought this is an opportunity to get into an industry that's actually rising rather than falling, because my previous life was in heavy engineering. And I won't bore everybody with that, but I've done everything from steelworks to cement plants, sugar factories, mines, mineral processing, quarries, you name it. So I've got a rather diverse background of experience, but I had worked up until I started Concoat back in '79. It was very much a family enterprise. The opportunity lend itself to growing something from nothing. And we started off purely as the distributor in the UK for Humaseal and rapidly became responsible as their European licensee. And we were delivering materials all over Europe. And that came to an end in 2005 when we sold the business to Humaseal. And I recommended that they retained my brother-in-law who was involved because he would fit their purposes well. But I had no desire to work for others, having spent too much time working for myself. And the circumstance presented itself for us to continue by splitting the company into two parts. The equipment side of the business really took off when I acquired the old multi-core SPCID from Henkel. As some of you may be aware, Henkel in 1999 went on an acquisitions splurge, and they finished up dominating the industry in rather a big way. Multi-core was a tiny part of that. The Dexter Hysol Corporation was another thing altogether, and many others. But when I took that over in 2002, it was because SPCID, which was Soldering Process Instrumentation Division, this was not core business to a group the size of Henkel. So I was then in a situation in 2005, 3 years later, having sold Concoat, which was a trademarked business, to Chase Corporation, Humaseal. I then thought, how can we then create the company? And I had two sons, I still have, pleased to say, one who graduated in mechanical engineering and the other who graduated in sports sciences. And this seemed to be the perfect opportunity to say, boys, might you be interested? No commitment. And the response was, yeah, why not? So I then blossomed the term, or christened the term, Gen 3. As you rightly pointed out, Mike, it is Generation 3. So my father started the business back in 1969.
Father, then you, and now your two sons.
Exactly. So from that standpoint, we started to get very much more involved or engaged from earlier days than that as to, well, if you put a conformal coating onto an electronic circuit, is it relevant to know what the hell's underneath it? And the answer to that is emphatically yes, it's critical.
Absolutely. You're locking all that, whatever's underneath it, you're locking it in. And
exactly.
Yeah.
But the problem is that paints and varnishes are not impervious to moisture.
That's right. They're all permeable, right?
They all breathe. They allow moisture and humidity to migrate in and out of the film. And if you've got something underneath that can attract humidity, the phenomenon we then call osmotic reaction is that the moisture permeates through the film, gets to that ionic contaminant that's underneath the surface, and the ionic matter converts to a liquid in various chemical conditions, and it creates a blister. So understanding that something underneath the coating, because of course, if anything went wrong, it was my fault. And getting rather tired of being accused of everything, it was appropriate to learn and understand everything relating to cleaning and cleanliness testing, which is exactly where I've been focusing all my efforts 100% since 2005. But my background goes all the way back to 79 because that's where we first kicked off in
Sure.
chemicals for electronics.
Sure.
Now,
So
what happened was
you'd mentioned a couple of things. I'm just going to jump in here for a second because I want to. I don't want to forget this. You mentioned something that just struck a note with me. You said that after you were working for yourself, you found it very difficult to work for others. I think entrepreneurs who start companies will make the absolute worst employees at some point because we are just used to doing things a certain way, whether it's bootstrapping or BSing or whatever it takes when your company is brand new to survive. And we just don't have time for nonsense, right? I mean, we will both be absolutely horrific employees if we were to go back into the work sector.
That is so true.
We'd be sacked in a moment. You did bring up multicore. I don't know if I do this accurately, but I do credit multicore to be the inventor of no clean flux, the original inventor of no clean flux through their X32. Am I remembering that correctly? Is that your recollection as well?
That is my experience. The man that invented them was Dr. Wallace Rubin, and Wally Rubin worked with me for a short time back in the year 2000, 1998, 1999, when we launched the world's first range of synergistically electrochemically compatible process chemistries. It was a pioneering effort, and it was thanks to a lot of work that was done by Wally Rubin. He invented the no-cleans together with work from Professor Laura Tabini. Laura, when I first met Laura, she was at Georgia Tech. Yeah. And she was, in fact, rather interesting segue, was in charge of a research project for the US Navy that was studying subsurface electrochemical migration. And she christened the term CAF. Wally Rubin and Laura Tabini were working together, and I was part of the groups doing all the research for removing CFCs and finding an alternative solution.
Were you part of the phase 2, the IPC phase 2 testing that tested alternate chemicals?
Yeah, there was a parallel program being run in Scandinavia by the IVF, the Swedish Research Institute, and they started first back in 1987. And through the Montreal Protocol, I always remember having a discussion with a dear old friend of mine, Professor Bill Brooks of IVF in Sweden. And I said, Bill, I don't understand how it is that a chemistry that was formulated and first really commercialized in 1947 has a makeup that is heavier than air, and it's all in the northern hemisphere. How did substance heavier than air migrate south across the equator, which is a dead zone, and then migrate vertically and create, as the experts believed at the time, the hole in the ozone layer? Well, we know a lot more about that these days, and I don't know that it was a real condition created by man. Hold that thought for another interview some other time, because I could go on for hours about this. But Bill Brooks really made sense to me when he said, I attended the lecture given by the British Antarctic Survey and the Norwegian Arctic Survey, and they were giving juxtaposed answers to the question. In one case, mankind faces a real crisis. On the other case, this is hokum. It's not going to happen. And Bill Brock said to me, well, I hear what you say, Graham, but the fact of the matter is we don't know. Can we take the risk to ignore it? And to that extent, I agree. So
and that began the business we're all in right now. That began the introduction of no clean, because necessity is the mother of invention. And when these offending solvents, or at least the accused offending solvents, were eventually banned, alternative solvents came onto the scene, some which were okay and some which were not. Alternative methods of cleaning, aqueous-based and other types of cleaning materials and methods came on the scene. But we were all, the majority of the industry, were given a get-out-of-jail-free card. And that was, hey, switch flux and maybe we don't have to clean. And
exactly.
Of course, if you have a choice between changing a process or eliminating a process, go for elimination. I always refer to that as kind of an implied contract with no clean. We had a contract with no clean when no clean came on the scene. We didn't realize it because we didn't read the fine print. But the contract with no clean is that the residues would be benign and invisible, right? That was what we were looking for. And at the time, boards were largely through-hole, surface mount. There was some surface mount, but was the size of giant trucks. You know, it was huge in comparison to today. I think what kind of made that process obsolete, the asterisk in the contract, was that as long as you promise to, I'll bring it into the common vernacular, socially isolate, socially distance your components, then everything will be cool. But I think what a lot of people really fail to consider is that when we stopped removing the flux, we stopped removing everything, right?
Mm-hmm.
And I think two things, and I've said this before, my audience will recognize this, and I say this on my lectures and presentations, is I would like the electronics world to recalibrate their thinking by stop calling it no clean flux. Call it low residue flux, because that's really what it is. It might be no clean if you choose not to clean it. But if you think it's no clean and then someone says you might have to clean it, you think you're doing something wrong. It's like tearing the labels off the mattress. You know, it says by penalty of law, don't remove this label.
Exactly.
And I think instead of calling it a defluxing process,
well,
call it a cleaning process.
Yeah, you hit the nail on the head, because what effectively happened is that all fluxes, as you and I know only too well, we compete in a small area of activity, and there's no shame in that in either sense. But what you have is fluxes leave residues. And one of the principal problems that has occurred is that, for a variety of different reasons, the most recent, of course, being lead-free, is that pretty much all process materials manufactured today incorporate non-ionic surfactant additives. And these materials, which are used very discreetly, are either used to enhance wetting or enhance de-wetting, as the case may be. And what they have done is that they have introduced, or they are by nature, an ultra-low surface energy material. Now, when you are dealing with residue removal, as you know as well as anybody on planet Earth, this can be an exacting task that is made worse when you're dealing with lead-free. Why? Because the temperatures by which you are manufacturing are higher, and the laminate that you are dealing with is becoming stressed thermally. And in doing so, what's happening is that the widespread use and embracing glycol materials means that we've now got ultra-low surface energy materials which are terrific at getting underneath low standoff tight spacing beneath components. The damn nuisance is they keep making smaller components that are being fitted almost flush to the surface of the board. And that presents a cleaning challenge, as you and I both know only too well, because having a low surface energy material allows you to get underneath those tight spaces. When it does its job, it breaks down that residue, and now you've got effectively what we happily call a porridge.
Right.
And how can you be sure to get the porridge back out again? And what it's also doing, and this was where Laura Tobini's work at Georgia Tech and her postgraduate, Brian Smith, if I remember correctly, and I am going back a number of years, what was happening is that the low surface energy materials are actually being absorbed into the laminate. And when you then get to lead-free, where your reflow temperatures are that much higher, you are now seeing a greater level of sucking up of those materials into the laminate. Now, within the laminate, you've got a hell of a lot of activity going on, not the least of which is that, of course, everybody is driving electronics to smaller and smaller, higher density packaging. And when you do that, you've got another problem, which is the increase of temperature, because that's the give off when you miniaturize stuff. So what's happening is that residues are being washed down in part. I'm over simplifying this, of course, but in essence, that is what is happening. And electrochemical migration is the more, or in my opinion, the most accurate term to use, as distinct from CAF, because CAF is really an extension of electrochemical migration, and it's happening subsurface.
Right. CAF, I like to, because I live near Los Angeles, I'll make this this topical or this geographic analogy. In the world of ECM, electrochemical migration, if electrochemical migration were a movie, the top billing star would be dendritic growth. That's pulling in all the ticket sales, right? Because it's dramatic. The co-star would be parasitic leakage, and a supporting actor, maybe even close to an extra, would be CAF, because CAF is there. It's there not all the time, but it's there frequently. It doesn't always cause a fatal problem. Lots of CAF events are unknown to the user of the board until it is known. Sometimes it makes its way up and becomes a star itself. I like to use that analogy because it's there, it's in the background. It may be no big deal. It may be a deal killer, but it's certainly there. And you're right, it's subterranean. Tell my audience what CAF stands for, and let's kind of dive into some of the causes of CAF and then some of the symptoms of CAF.
Well, if you will forgive me for doing so, I published a book through our friends at iConnect 007 last year that I'd encourage everybody to download and take a read, because a heck of a lot of work went into producing that and trying to make sure it was correct.
And for my audience, I'll put that information on where to get that book in the show notes. So
terrific. Thanks for that.
That'll be there.
So what I said in that book, and I will ask for forgiveness that I read from this. A CAF failure is where copper corrosion within a printed board leads to a short. It is electromigration of the copper from anode to cathode between two conductors of different potential. This is the opposite of the SIR failure, where a short grows from the cathode to anode and typically forms a well-known dendritic structure. The phenomenon is sometimes referred to as cathodic anodic filament because, conversely to SIR, electrochemical induced short grows from the anode to the cathode. The short is also a metal compound, a salt, and needs to be hydrolyzed to conduct. Hence, a CAF short can vanish when removed from a damp heat environment. there is a lot of confusion as to what it is. And the best way to keep everybody on the even keel is to say, look, it is electrochemical migration subsurface. How does it get there? And if one thinks about the way in which a printed circuit board is fabricated, you've got multi-layer fabrication going on pretty much everywhere now. I don't know what the latest layer count is, but I know of companies that are already doing 34 layer boards. And of course, you've got drillings for connection that's within the laminate, and those drillings to create the through-hole vias through which the connections can be made, copper barrel loaded. And every one of these particular manufacturing functions are imparting physical stress. And what happens, of course, when the laminate becomes stressed is that you've now got an increased pathway through which low surface energy chemistries can migrate more freely. And when you electrify, they carbonize. And bingo, you've got a problem. So it's not easy to explain other than when you drill through the laminate, what happens? It is not cutting. It is smashing its way through. And of course, the condition of the drill probe itself is critical to minimize the amount of, as it were, collateral damage that's being imparted. Now we've got the industry looking at ways, of course, cutting costs, improving profitability, which is a perfectly healthy thing to do. And what's happening is that they are faced with the problem of, well, we've got to do selective soldering. Can we get rid of it? And the answer had been, and is, very much, let's go for press-fit connectors. Well, you go to press-fit connectors, and this is the classic square peg in a round hole. And we all know what happens in that situation. And the pressure that's being imposed to fit those connectors is certainly more than sufficient to actually cause crazing around the copper barrel fillings on the through-hole vias, and bingo, you've got a pathway for failure. What has also happened is that through those stresses, tin-rich alloys that are used in the soldering process, well, tin-rich, their plating processes for those through-hole vias were tin-rich, let's just put it that way. Well, Continental Automotive made a presentation to the industry about 18 months ago, and they had changed their manufacturing process from tin-rich to indium in order to offset a new condition that everybody had failed to appreciate, which is tin whiskering. And tin whiskering is a phenomenon that is becoming much more widely known, and it's not a great idea to be imparting all of that stress. But let's take the alternative route. So, well, we won't do press fits, we'll do selective soldering. Okay, this is a good thing, but the temperatures required by using lead-free alloys is that much greater. And again, the laminate becomes stressed, thermally expands. Like anything that gets hot, it expands. You and I are suffering from that from time to time, I know.
Must be 1,000 degrees by now because we keep expanding.
Exactly. Thank God this isn't on a video.
That's right. I've always said I have a face for radio.
So true. And so the situation is kind of one of these interplays of problems. But now let's talk about high density packaging, because I don't know whether your business is involved, but we're very much engaged with HDPUG, the High Density Packaging Users Group, and this is a kind of an offshoot in the US, where we are investigating some of these phenomenon and trying to understand the causes, and from that identify the means by which we can test for it and provide a service that allows the customer to evaluate the best approach for their requirement. But to go back to high density packaging for a moment, as I mentioned earlier, the energy give up from that is increased operating temperature on the board. And minute amounts of residue can create incredibly vicious reactions because the heat condition. I've got customers that are right now manufacturing, and have been for some years, actually for Halliburton, on the drill probes that are used for the oil exploration and gas exploration industry. And they cannot have any failures, zero. And they are here in the UK, a good friend of mine runs that. They are producing electronic circuit assemblies with zero defects that are operating at greater than 175 degrees C. And that is hot for continuous operation. And it's an incredibly harsh environment as far as physical activity, vibration is concerned. So they have effectively created their own techniques, especially for direct die attach. So now when we think about residues being present on high density packaging and the miniaturization that's going on in the industry, we've got a new set of parameters that we have to take on board. But the increased heat means that the presence of residues becomes supercritical. And anybody listening to this, I can assure you, if you're not doing it now, you will be doing it soon, and that is to go back to doing cleaning. You have no choice. And all of the evidence is pointing us in that direction. So for you and me, Mike, we're okay.
Yeah, well, we're going to work tomorrow. Yeah, for sure. So let me just kind of do a recap. So because a lot of this is maybe new to our audience here. One of the primary differences between CAF, which is subterranean, below the surface of within the layers of the board, and just normal ECM dendritic growth, is one technical difference. The filament grows on the surface of the board from cathode to anode. In the middle of the board, it goes the other direction, which is just a technicality. That doesn't affect really anything. The three things that are required on the surface for ECM, for dendritic growth, for example, is moisture, a conductive residue, and electrical current, a bias. There are four elements required for CAF. Those first three, plus a pathway. Of course, on the surface of the board, it's all pathway, right? It doesn't have to burrow down, doesn't have to tunnel. So your point was that the pathway for CAF, for a filament to exploit the pathway, can be created by the drilling process, particularly dull drills. Friday afternoon, I have a hot date Friday night, push the drill, press a little harder, don't change out the drill bits, etc. Thermal excursions can exacerbate that. I know we didn't talk about this specifically, but inadequate resin flow, or sometimes called dry weave, can create vulnerabilities within the layer of the board that can end up in these little gaps, these little, I like to call them micro cracks, for lack of a better term.
You and I are on exactly the same wavelength. The situation that we have is that, how can I best wait? We have an almost symbiotic relationship with the British National Physical Laboratory. And they do all the science research, and from it we have developed and evolved test methods and apparatus that I'm then taking to the marketplace. And what we got involved with recently was a major research study to evaluate CAF and try to figure out ways in which we can mitigate against it. And the first meeting we attended, and I am listening to a room full of highly educated and knowledgeable engineers from all over the world. And they said, well, and much of this was new to me. The individual glass fiber strands are typically between 9 and 11 microns in diameter. And I said, forgive my asking a dumb question, but what grade of glass do you use for that? And the reply came, E-grade glass. And I said, but E-grade glass is, to the largest extent today, made up of recycled material. Oh, how did you know that? I said, because in my previous life, we also made glass processing plant. Oh, so I did suggest that it would be worthy of consideration to investigate using a higher grade of glass and see if that improves the situation. And I can tell you that that certainly has been taken up and it has improved the situation. And as you rightly said, Mike, the weave is one thing, the resin fill is another. And Carl Salter, the chairman of the CAF committee at IPC, I'm Carl's vice chair, he kind of explained it that this is why we created the Manhattan distance that's gone into the CAF test method. It's not perfect, but it certainly does the task of trying to make sure that where you drill relative to the density of the weave and the resin filling that's taken place, that's going to be an important factor to improve the CAF resistance, if you wish, from the laminate. Everything else, I think we've kind of covered. It's that there are always a multiple set of reasons for electrochemical failure. But as you rightly say, you need those three key elements, plus in the case of subterranean, yep.
Yeah, I'd like to tell people you have two choices when it comes to CAF. Obviously, we're both in agreement, and you said it earlier, when we're talking about surface level ECM, clean your way out of it. No big deal, right? That's kind of conventional wisdom once again. When it comes to CAF, you can't clean your way out of CAF because you can't reach it. So there are two choices. One is a reactive choice, which is to bake your boards, because if you can remove moisture, you can't have ECM without moisture. That's easy to do when the board is first finished in production. It's a little harder to guarantee that it won't pick up moisture in its operating environment. But the best thing is to use CAF resistant laminate materials. And just a little anecdote, and I'd love to hear some anecdotes from you too. And my audience may have heard this before, so sorry for those that have heard it if this is repetitious, but it's right in line with what we're talking about. I was hired as an expert witness in a civil litigation matter between an OEM and their contract manufacturer for basically, here's how to build the board. Here's what we want. Oh, you did what we want? We're going to sue you because everything failed. But they had a CAF issue, and this board was located in the ground. It had a battery, a 10-year battery that would operate this board and send a radio signal up to a nearby receiver that was connected to a power source. After about 6 months, all the boards started failing, and it drew the battery down, right? It drained the battery because they had some unintended conductivity, not enough to create a dramatic short, but just enough to drain the battery. And it turned out to be CAF. And when I was hired to go through all the documents and email chains, and it was very interesting. When I looked at the statement of work from the IP holder to their subcontractor, part of it was they wanted the contract manufacturer to also have the boards made, right? So, and under the materials for the board, here is the verbatim description of the board material: down and dirty FR4, nothing special. That was it. So I was like, okay, are there any IPC slash sheets that say down and dirty, nothing special? But that set the tone that they didn't really care, just cheap down and dirty, nothing special.
Yeah.
And of course, the boards failed. They had to, I think 50,000 boards were recalled or something like that. It was a multi-million-dollar lawsuit. Everybody loses, there's no winners in those things. And they didn't bake. They potted. So they thought they were, to your point earlier, they enclosed this board in a box about the size of a hockey puck and filled it with black silicone. And they thought that because they had protected it from the evil elements, nothing could get in. What they didn't do was clean their boards after a certain type of soldering. They potted their boards without baking, without cleaning, and they basically just built a cage for all the bad actors to do this like MMA fight. And all these bad actors did what they do, and they had no way to outgas. They couldn't get out. So they just caused trouble on the board.
You're absolutely right. And part of the experience, from my personal life experience, and I picked up a big typo error in our website when it claimed that I had been in the industry from 1929. But there are days that I feel now that perhaps I do go back a long way.
Yeah, your spirit goes back that far.
But in heavy engineering, we were steeped in standards and huge amount of experience going back over 200 years. And I migrated into the electronics industry, and I couldn't believe that when I entered it, and was 1979, you guys aren't even metric. Holy smoke. And I had to reset everything from being metric back into imperial measurements. But the most important or impressionable event for me was I had to liken the electronics industry at that stage as the life of a person. And in the life of a person, the electronics industry back then was an infant, a babe in arms. And now, what are we, 40 years on? We are, I think, in as an adolescence. We've still got some way to go. Education is paramount. Passing on the wisdom, the experience, the background that you and I have had is imperative for the future of the industry. I'm very much engaged with the mentoring program that IPC put forward, and I gave a presentation at the conference back in Apex in February this year.
Which was, by the way, about 12 years ago.
Yeah, exactly. But I could not help but be so enthused by the attentiveness and the reception of these young people. They are really switched on, bright people. And it's only beholden upon us to transfer that knowledge to them. So
that's right. We have a another prior guest on the show referred to as a silver tsunami, which is all of us leaving, right? And for the longest time, there was not a lot of replacement. I didn't see a lot of young blood coming into this business, and I'm seeing it now, as you are. I think I noticed it back in 12 years ago, back in February, when I was at Apex as well. I saw more young blood, and I also became a mentor through that program, which was great. But I think one of the reasons I started this podcast was to capture some of the greatest minds in their field and their technical advice and their knowledge, so that others can hear about it later. Because what a lot of companies are unfortunately doing, it's just economic reasons, I suppose, is, there used to be like the old sage. Every company had their old sage that knew where all the process skeletons were buried and has been around a long time. And their job is basically to answer questions and troubleshoot, and they know it. They're retiring and they're not being replaced by another old sage. So there are not a lot of process experts. For example, if we look at Rockwell or Collins now, Doug Pauls and Dave Hillman, which, Dave's a metal specialist, and Doug is the king of conformal coating for that group, and every division of that group reaches up to him for advice. When he leaves, will there be an internal person who just knows that subject like the back of their hand? Maybe, maybe not. So I think what happens when they don't have an internal source, they seek external sources, which are, sometimes good people like yourself who know what they're talking about. And sometimes it's someone trying to hawk a piece of hardware that is the wrong hardware for that problem. And, they don't really get unbiased, non-commercial answers to their questions. So this podcast is designed to, not hawk machines, but to, provide good process knowledge. And hopefully this and other like IPC webinars and SMTA webinars and knowledge bases, hopefully all that will be there for the young ones, right?
I completely agree with you, and you are doing a tremendous service to the industry. It's fun. I don't know about you, Mike, but I still get a kick out of this.
I don't have a great work ethic. If I am bored, I just don't do it. So, yeah, it has to be fun. Otherwise, I wouldn't do this, right?
I can't stop myself from just dreaming up something else to get involved with. My situation is that I was technically retired about 5 years ago, but I don't want to retire. And
Nice try. Nice try. Yeah.
Yeah. And my younger son, to fair play to him, he stood up to the plate and he's now running the business on a day-to-day basis and doing a cracking good job. And he's only 32. So that's a real bonus as far as I am concerned.
Sure.
But when I left the building for lockdown back in March, his words reverberated around my head. And stay out.
Yeah. Good luck with that. Yeah. You're doing all the background stuff.
That I have had the benefit throughout lockdown of being able to devote a disproportionate amount of my time to helping the industry with new standards. And the subject matters that I've been dealing with, I kind of naively perhaps thought that harmonizing standards between IEC and ISO and IPC would be worthwhile. And well, okay, commercial considerations have suddenly raised their ugly head, but new standards are about to be issued. We've got 2 new ones coming out from IEC, which is a follow-up to 2 other studies. About PICT, the process ionic contamination testing.
Mm-hmm.
We developed that in conjunction with a collaboration with Robert Bosch in Germany. And for the first time ever, we have an instrument that has Six Sigma verification, which from a QA point of view is exceptional. Nobody else has ever done that. And forgive me for mentioning it, Mike, because that gets you right in the plexus.
No, that's worth mentioning.
But it's really important, and the beauty of it is that you can control your process using an instrument that's at least as sensitive as ion chromatographs. In fact, the next generation of the instrument, which we're working on right now, is going to take us into nanosiemens levels of sensitivity. So the instrument will become even better. But the most important point for me to put across is that you can do the process control in less than 15 minutes.
Yeah.
Using other techniques such as ion chromatography, FTIR, SIR, they are just not suited to that particular role because it takes too long. And more importantly, you need really clever people to do the testing.
Right.
It's
Right.
very easy.
It's not quite a plug and play. Those other technologies, you need an engineer or at least a technologist to run those types of equipment.
Absolutely.
The other types. Let's. We only have a few minutes, so I just want to kind of put a bow on this conversation here. CAF, of course, subterranean. We talked about that. We talked about the four causes of CAF: moisture, conductive materials, which are usually plating solutions, and electrical bias and a pathway. If the best way to mitigate CAF is to prevent CAF, and the best way to prevent CAF is to use materials that cannot provide a pathway, because we really can't mitigate against all moisture. We really can't mitigate against electrical current. We really can't mitigate against conductive corrosive materials, because that's just part of the plating process. So number one, CAF resistant materials that will not fall apart and open a pathway that filament can exploit. The second, if you don't have the ability to use those better materials, then baking is really the only thing that we can reach in, and the only substance we can remove by a baking process is moisture. We can't remove the conductive materials or anything else, or we can't fill in the pathway after it's there. So baking would be a good process, and then some mitigation to make sure that it doesn't pick up moisture in the future. There is also an IPC standard, test method 650-2625, which is the CAF resistance and other internal electromigration testing protocol. There are machines, I think you make one of them, called AutoCAF, which can test for CAF. There are analytical tools made by other companies, one of them called Sherlock, which purports to look at your board design and kind of calculate the propensity of CAF based on a number of factors. So am I wrapping that up properly?
I think you're wrapping it up really well indeed. My only add-on to that, I guess, is that yes, I think there's a lot of confusion about CAF and subsurface electrochemical migration as distinct from SIR. The measurement technique is the same. It's measuring changes to resistance. And in doing so, you need instruments that have that capability to measure at picoamp, nudging, as we are and so are others, at femtoamp levels. But on the other hand, we've got a real problem. And as you are aware, I've recently taken over as the vice chair of the 5-30 Cleaning and Coating Committee for IPC. And in that regard, we have some problems to deal with in the context of electrochemical migration and the behavior, the robustness of the circuitry, by saying, look, on the one hand, we've got the drive for electric vehicles in Europe and China. This is rampant. And that is ultra high voltage, pretty high current loadings, and we have limited amount of knowledge and understanding of all of the facets relating to that. But testing at 1,500, 2,000, 3,000 volts for anything up to 2,000 and 3,000 hours is the need that's been identified by the experts. Now, on the other hand, I've got customers such as ESA and NASA and medical electronics, where they're looking at ultra low voltage, ultra low current, and they in themselves present some interesting challenges. So as chair of the 532B SIR ECM task group, I've put forward a structured development program, and I would encourage anyone listening to become involved in that. Take a look. The program is there for everybody to have a read, and certainly please pass comments, because we need to have the support to carry out the research necessary for the future of our industry.
Well, very good. I appreciate the work you're doing on that committee and all the other work you've done. Thanks for being my guest today, Graham. And I wish you so much luck that eventually we'll see a Gen 4 and a Gen 5. You're just going to have to keep changing your company name as your grandkids start to take over.
Yeah, we don't have any that we know of. Not yet. But Mike, it's been my pleasure. Great honor to participate with you, and thank you for hosting this. Very much appreciated. And I'll look forward to hopefully seeing you in the new year. I don't know that it's going to be in the early part, but let's just look forward to having a drink or two together next time we get face to face.
That sounds good, and we don't have to limit it to two. I think we all deserve. I was recording another episode yesterday with a group of people, and we were talking about the celebrations we'll have when this thing is truly over. I don't think anything will be invented. I don't think anything will be produced for 6 months, because I think everyone's just going to take a well-deserved holiday, have a well-deserved drink or 10, and celebrate for a while.
Yeah,
we've all earned it.
I'm just thankful that our wine merchant delivers.
Yes, exactly. Yeah. Well, our restaurants here in California are all offering, takeout, obviously. And somehow they got permission from the alcohol authorities, called ABC, to provide drinks to go. So you can get margaritas and wine and all sorts of things in little plastic cups with plastic lids on them to take away in your car.
You and I did have an exchange on email about you making a visit down to Guadalajara in Mexico. And my response to you was 1 tequila, 2 tequila, 3 tequila floor.
Yes, that's right. Yeah, that was Cabo San Lucas. Yeah, I was there 2 weeks ago for a little bit of a break. And yes, exactly. It is interesting how when you sit by a pool and it's 80 degrees and you're sipping tequila, COVID just goes away, at least in my mind, right? There's no pandemic. There's no problem.
I suspect that CAF goes away too.
All problems go away until the next morning, and then, reality comes back. Now I'm back in my host chair and, all that. So yeah, reality does return. It has a way of doing that. Well, Graham, thanks again for being my guest. Thanks for imparting all that wisdom to my audience. And for my audience, if you'd like to get a hold of Graham, I'll just go to the show notes on Spreaker.com, Spreaker.com. Look up Reliability Matters. There's so many ways to get this podcast. I don't know if you're getting it on Spreaker or through Apple Podcasts or Spotify or iHeartRadio or whatever. But only Spreaker has the show notes, and the show notes will have Graham's contact information. And I know Graham well enough that if you ask him a question, he will be very excited and want to provide a reply. That's just the way he is. So thanks again, Graham, and thank you, my audience. We'll talk again very soon.
Thanks again, Mike. Bye now.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. We release new episodes on the second and fourth Tuesday of each month. Don't miss an episode. Subscribe to Reliability Matters on Spreaker.com, Apple Podcasts, Google Podcasts, Spotify, and virtually wherever you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat, who syndicates this show at PCBchat.com, and where you can also listen to Editor-in-Chief Mike Butow discuss interesting topics with industry leaders. You can also listen to the show on Ascendo Reliability at reliability.fm. This show and many other reliability-based podcasts are available there. Thanks again for listening. We're going to take a break for the holidays. This is our last show of 2020. We'll be back on January 12th with 2021's debut episode, featuring a conversation with Dr. Eric Fossum, the inventor of the CMOS image sensor, otherwise known as the camera on a chip. We had a very interesting conversation. Don't miss it. In the meantime, I wish you happy holidays, stay safe, stay healthy, stay happy, and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.